There's a very specific, a very modern kind of nightmare that I think a lot of us have either experienced or we definitely fear experiencing. It isn't like monsters under the bed. It's the check engine lightmare.
Yes. The little orange icon that just completely ruins your week.
Exactly. You're driving along, minding your own business, and the car starts making this noise. It's a grinding, a shuddering sound. It sounds like I don't know, a lawnmower trying to digest a bag of marbles.
Mm-hmm. Not a good sound.
Not a good sound at all. So, being a responsible adult, you take it to the mechanic, they hook it up to the big computer, they run every single diagnostic tool they have in the shop. You sit in the waiting room drinking that terrible coffee for like 2 hours.
The worst coffee.
The worst. And then the mechanic comes out, wiping his hands on a rag, and he smiles at you.
And let me guess. He says, good news. The computer says everything is fine.
That is exactly what he says. Structurally, he tells you, the car is perfect. The pistons are fine. The belts are tight. You are good to go. But then you get back in the car, you turn the key, and the noise is still there.
It's still there.
It's grinding. It's shaking. But now you have a piece of paper from an expert telling you that you're crazy.
That is a terrifyingly accurate analogy because, for a car, that situation is just, it's annoying. You turn up the radio and you try to ignore it. But when that same scenario plays out in the human body, and unfortunately it does for millions and millions of people, it is absolutely devastating.
And that's what we're talking about today. We're talking about chronic pain. But I want to be really specific here.
Yeah.
We aren't talking about I fell off a ladder and broke my leg pain.
Yeah.
We're talking about the kind of pain that defies the MRI. The kind where the doctor looks at the x-ray, looks at the blood panel and says, there is nothing wrong with you. Structurally, you are fine. And then they deliver that crushing line, the one that feels like a door just slamming shut in your face. You just have to learn to accept it.
Pain acceptance. It is such a heavy phrase. It essentially means we have reached the end of our knowledge, so this is your new normal now.
And, unfortunately, it is an incredibly common experience. If we look at the statistics, specifically from the Heslop and Wright review we're covering today, chronic pain is affecting something like up to 40% of individuals in the U.S.
40%. That's staggering.
It is a staggering number.
It's almost half the people you see walking down the street.
It is. And a huge portion of those people are living with that check engine light blinking, while the entire medical system is frantically looking for a broken piston or a snapped belt. They're looking for structural damage. They want to find the broken bone or the torn ligament they can point to.
But, and this is the core mission of our deep dive today, what if the mechanic is looking at the wrong system entirely? What if the problem isn't the parts? What if the problem is the fuel? That is the shift. That right there is the aha moment in the research we've gathered for this. We're moving away from viewing chronic pain solely as a structural issue, a broken part, or even just say a viral aftermath. We are looking at compelling molecular evidence that for many, many people, chronic pain is actually a form of metabolic dysfunction.
Metabolic dysfunction. Now, I have to stop you there because metabolism is a word that gets thrown around so much. Usually when people hear metabolism, they think about weight loss. They think, can I eat this pizza without it going straight to my hips?
Right. We tend to think of it purely in terms of waistlines and, burning calories.
But that's not what we're talking about here. We are talking about something much, much more fundamental, aren't we?
Oh, much more fundamental. We are talking about cellular bioenergetics. We are talking about how your nerves, the actual wires of your body, how they process energy to function. The hypothesis we are unpacking today is that the pain signal, it isn't a glitch in the software. It isn't just a random error. It's a cry for energy. It's a distress signal from a nervous system that is, in essence, starving.
Wow, that is a fascinating and slightly terrifying concept. A starving nervous system. It creates this image of the nerves just screaming because they're running on empty.
Precisely. It brings up the possibility that the nervous system is hyperexcitable, not because it's damaged, but because it is fueling itself so inefficiently.
Okay, let's unpack this, because today's deep dive is going to take us into some really specific biology. We aren't just going to say eat healthy in that vague eat your veggies kind of sense. We're going to look at the molecular machinery.
Right. We have to get granular. So we're going to look at three main pillars today. First, we need to properly define what this mystery pain actually is. It's a category called nociplastic pain. Then we need to understand this concept you brought up, the pain doom loop, and how the brain gets stuck in it.
And finally, the solution that all this new research is pointing toward, the metabolic reset. specifically how a ketogenic diet, and again, we're talking medical keto here, not just the bacon and butter fat diet, how it can change the very fuel source of your neurons to physically stop the pain signals.
And we have a really great stack of sources to guide us. We've got articles from Pain Medicine, a really moving patient account from The Guardian about a woman named Natalie Mead, which is just incredible. We also have some deep research on fibromyalgia by Dr. Miguel Papola, and these really detailed reviews on things like adenosine and cellular biology from Frontiers in Nutrition.
So buckle up. We are going from the doctor's office down into the mitochondria and all the way back out again. Let's start with the problem itself. You mentioned this term nociplastic pain. I feel like I've heard of nociceptive pain and neuropathic pain. What on earth is nociplastic?
It is a relatively new term, actually. It was formally adopted by the International Association for the Study of Pain only around 2017. So before that, it was all a bit of a gray area, really. To understand it, it helps to look at the etymology. It comes from the Latin nocere, which means to hurt, and the Greek plastos.
Plastos, like
Plastic.
exactly like plasticity, moldable, formed. It means malleable pain. The classic definition is pain that arises from altered nociception. That's just your pain processing system, despite no clear evidence of actual or threatened tissue damage.
Okay, so let's go back to our car analogy for a second. A nociceptive pain would be like a flat tire. You can see it. It's obviously broken. Correct. That's straightforward tissue damage. You cut your finger, you break a bone, that's nociceptive. Neuropathic pain would be like a cut wire in the dashboard, actual damage to the nerve itself, like in sciatica or diabetic neuropathy.
But nociplastic pain,
Yeah.
the tire is full, the wires are all intact.
The hardware, the tissue, the bones, the nerves themselves, it all appears fine on the scans, but the software, the processing system, is glitching, it's malfunctioning. In the past, this was often called central sensitization. It means the volume knob on your entire pain system has been turned up to 10 and the knob broke off.
And what's the poster child for this kind of pain? Is there a classic example?
Fibromyalgia is the absolute classic example. You have this widespread pain, this crushing fatigue, sleep issues, and that cognitive fibrofog that people talk about. It can exist on its own, or it can ride along with other conditions. But the key is that the level of pain is completely disproportionate to any physical injury you can find.
It's interesting you use the volume knob analogy because that implies that the signal is real. It's just, it's amplified beyond all reason.
Well, that is such a crucial point. Patients with nociplastic pain are so often told, either explicitly or implicitly, that the pain is all in their heads. And, technically, yes, the processing is happening in the brain, but the pain is real. The suffering is real. The experience is absolutely real. It's just that the trigger isn't coming from the outside world. It's coming from an internal amplification error.
Which brings us perfectly to our case study for today. This story, for me, really grounded all the science. It takes it out of the textbook and into a real person's life. It's about a woman named Natalie Mead, who wrote this incredibly powerful piece for The Guardian.
It is a powerful story. And it's a story that I think will resonate with anyone who has had to navigate the medical system with a mystery illness.
So let's set the scene. Natalie is 27 years old. She's young, she's healthy, vibrant, she's doing everything right. Then one day she gets a migraine. And we've all had headaches, right? Maybe even a bad migraine here and there. You take a pill, you lie down in a dark room, and eventually it passes.
But this one didn't pass.
No. 10 months later, the migraine was still there. Can you even imagine that? A single headache that lasts for nearly a full year.
It's unimaginable torture. Medically, we call that chronic intractable migraine. It's just relentless.
Exactly. For years, she lived with this. And she went through the absolute ringer. She saw all the specialists. She got the scans. She took all the medications. She did the crazy elimination diets where you're eating nothing but like rice and pears for weeks. And eventually, she got that diagnosis we just talked about, central sensitization.
Right. Which, in the context of her treatment, basically just meant her nervous system was stuck in an overactivated state. It's a descriptive diagnosis, but it doesn't really tell you why it's happening. It just names the problem.
Right. It's a label, not an explanation. She describes it as her brain creating migraines ex nihilo, just out of nothing. And she talks about this concept of the pain doom loop. I think that phrase is so incredibly evocative, the pain doom loop.
It really is. And biologically, it's actually quite accurate.
So how does that loop work? How does it get started?
Well, it's a vicious cycle. The pain itself, the sensation of pain, sensitizes the nervous system. Because you're in pain, Your system becomes hypervigilant. It thinks you are constantly under attack or in danger. So, to protect you, it lowers the threshold for firing.
It's trying to be helpful. It thinks it's doing you a favor.
Evolutionarily, yes. I mean, if you have a broken leg, your body absolutely wants you to be super sensitive around that area so you don't walk on it and make it worse. But in chronic pain, this protective mechanism gets stuck. The threshold drops so low that things that shouldn't hurt, like light, sound, or even just mild pressure from your clothes, start to register as painful. That phenomenon is called allodynia.
So the pain causes the sensitization, which then causes more pain, which then causes even more sensitization.
Precisely. It is the very definition of hyperexcitability. The neuron is just sitting there with a hair trigger, ready to fire at the slightest provocation, and once it starts, it doesn't want to stop.
And the standard medical advice she got was essentially, this is your life now. Practice acceptance.
Which is an incredibly difficult thing to hear when you are in your 20s and in constant debilitating agony. It just feels like giving up.
But this is where her story pivots, and this is where we move from the wiring to the fuel. Because Natalie didn't accept it. She kept searching and eventually met a neuroscientist named Dr. Kyle Bills. And this is the moment that changes everything for her. Dr. Bills didn't look at her nerves. He didn't order another MRI. He looked at her blood sugar.
And this is a really critical distinction. He wasn't looking for diabetes in the traditional sense. He wasn't looking for a disease that had already, destroyed her organs. He was looking at the dynamic function of her metabolism in real time. He had her wear a continuous glucose monitor, a CGM.
Right. These are those little white patches you see people wearing on the back of their arms now. They seem to be everywhere.
Exactly. They track your blood sugar 24/7, not just at that one moment when you prick your finger. It gives you a moving picture, not a snapshot.
And what did he find? What did that moving picture show?
He pointed to what he called sawtooth zigzags on her graph. She was experiencing these massive spikes and then these crashing dips in her blood sugar all day long. Specifically, she was dealing with something called postprandial hypoglycemia.
Postprandial, so after a meal, that's the energy crash after you eat, right?
Yes. You eat a meal high in carbohydrates, your blood sugar spikes way up, your body releases a flood of insulin to handle it, and it overcompensates. It shoves too much sugar out of the blood, crashing your blood sugar down way too low.
And Dr. Bills connected this directly to her migraines. He saw a causal link there.
He did. His theory, and this is backed by his research, is that the electric storm of a migraine can be triggered when this blood sugar dysregulation completely overwhelms the hypothalamus.
The hypothalamus. That's the brain's sort of
Yeah.
master control center for hormones and energy balance, right?
Exactly. I mean, you have to think about it this way. The brain is an energy hog. It uses about 20% of your body's total energy, even though it only weighs a few pounds. Crucially, it has no energy reserves. It can't store fat like your thighs can. It needs a constant, steady, unbroken stream of fuel from the blood.
So if that fuel supply suddenly cuts out,
It's panic, absolute panic. If the brain sees its fuel supply crash, which is exactly what happens in hypoglycemia, it interprets that as a mortal threat. It's a starvation signal. It triggers a massive stress response. Adrenaline, cortisol, the whole fight or flight package gets deployed.
and for someone who already has a sensitized nervous system.
That stress response acts like a match in a powder keg. It's the trigger that sets off the migraine. So
Yeah.
it's not just a glitching nervous system anymore. It is a metabolic failure.
That is such a huge shift in perspective. It's not my nerves are broken, it's my nerves are starving.
And this isn't just one person's anecdote. This connects directly to the research by Dr. Miguel Papala regarding fibromyalgia. He published a study that effectively asks the question, is fibromyalgia actually brain diabetes?
Brain diabetes, wow, that is a phrase that will wake you up. Tell us about the Polis study.
So Dr. Papala and his team looked at a group of patients diagnosed with fibromyalgia, and they had this central hypothesis that insulin resistance, which is the hallmark of prediabetes and type 2 diabetes, was causing something called cerebral hypoperfusion.
Hypoperfusion, meaning not enough blood flow.
Correct. Low blood flow. We know from lots of other research that insulin resistance damages small blood vessels. It makes them stiff and less responsive. If that happens in the tiny capillaries of the brain, you get these areas that just aren't getting enough oxygen and enough nutrients.
So what did the data show? Did it support the hypothesis?
This is the really shocking part. In his study of 13 fibromyalgia patients, all 13 of them had at least one clear marker of insulin resistance.
All of them, 100%. Yeah. You almost never see 100% in a biological study. That's unheard of.
It is incredibly rare, and here's why that finding is so important. Standard tests often miss this completely. 4 of those patients had a perfectly normal HbA1c.
Okay, let's pause there. HbA1c is the standard blood test you get at your annual physical, right? It's the main screening tool.
It is. It measures your average blood sugar of the last 2 to 3 months. If it's below 5.7%, the doctor usually stamps your chart healthy and sends you on your way.
So these patients would have been told, your metabolism is fine, nothing to see here.
Exactly. But when Papola and his team ran deeper, more sensitive tests, specifically the HOMA-IR and QuickEye scores, they saw the truth that the A1C was hiding.
HOMA-IR. That sounds complicated. Why is that a better test than the standard HbA1c?
I like to use an analogy. Think of it like a duck gliding smoothly across a pond. The duck moving across the surface, that's your blood sugar. It looks calm, stable, everything's fine. But if you look under the water, the duck's legs are paddling furiously just to keep moving. HOMA-IR looks at the legs. It measures how much insulin your pancreas is having to pump out just to keep that blood sugar looking normal.
I see. So the sugar level looks normal, but the body's screaming, working overtime, just to keep it there.
Precisely. These patients had massive amounts of insulin flooding their systems, a state called hyperinsulinemia, just to maintain that equilibrium. Their bodies were under immense metabolic stress.
So they were profoundly insulin resistant, even if their average blood sugar hadn't technically crossed the diabetic threshold yet?
Correct. And Papola's argument is that this insulin resistance directly affects the brain regions that process pain places, like the thalamus and the insula. These regions are essentially struggling to get and process energy because the insulin isn't working properly to get the fuel into the cells.
It connects right back to that pain doom loop again, doesn't it? Because if you're in constant pain, you're constantly stressed. If you're stressed, your cortisol goes up. If cortisol goes up,
Your insulin resistance gets worse. Cortisol directly blocks insulin's action. It's a bidirectional relationship, a true vicious cycle. The pain induces insulin resistance via the stress response, and the insulin resistance may cause central pain through small fiber neuropathy and that low blood flow we talked about.
so, okay, we have a very clear problem here. The nervous system is hyperexcitable, and it's being fueled by a metabolic system that is spiking and crashing all over the place, causing inflammation and, effectively, starvation in key parts of the brain.
Which brings us, finally, to the solution that Natalie Mead found, and what these researchers are now seriously exploring: the metabolic reset.
And do the ketogenic diet. Now, before the listener rolls their eyes, because, let's be honest, keto is slapped on everything from weight loss shakes to candy bars these days, we need to be very, very clear. We're not talking about diet culture here. We're not talking about getting a beach body.
No, absolutely not. We are talking about the ketogenic diet as a form of medical therapy, and this is not new. This was developed back in the 1920s at the Mayo Clinic, specifically to treat epilepsy in children.
For stopping seizures, right?
Right. Before we had all these sophisticated anti-seizure drugs, we had keto. It has this incredible ability to stabilize the brain during these electrical storms. And since migraines and a lot of chronic pain states share features with epilepsy, that core problem of hyperexcitability we keep coming back to, the translation makes perfect sense.
So how does it actually work? Because it's got to be more than just sugar is bad. There are specific mechanisms happening at the level of the neuron. It sounds almost like biohacking your own nervous system.
It is biohacking in the truest sense. You are fundamentally changing the inputs to change the outputs. There are several powerful mechanisms at play, but let's start with the big one, the fuel switch. This comes right from the Heslop-Wright review.
Okay, lay it on us. What's the fuel switch?
So when sensory neurons are stressed, let's say by a chemotherapy drug or a chronic injury or even just metabolic dysfunction, they shift their metabolism. They move toward a state of aerobic glycolysis.
Glycolysis, that's just burning sugar, right?
Yes, but it's burning sugar really rapidly and very inefficiently. It's a stress response. It produces energy quickly, but it's what you might call dirty energy. It generates a lot of waste products like lactate and reactive oxygen species. This metabolic state is intrinsically linked to pain signaling.
So a pain neuron is a sugar-hungry, inefficiently burning neuron.
Exactly. It's hyperactive and inefficient. Now, the ketogenic diet forces a hard switch. By severely restricting glucose and eating primarily fat, you force your body to produce ketone bodies. The neurons then have to stop using glucose and start using ketones for fuel. This shifts them back into a much more efficient process called oxidative phosphorylation.
Okay, I think I need an analogy for that.
Sure. Think of glycolysis in a stressed neuron like burning damp coal in an old steam engine. It's fast, it's hot, it's incredibly dirty, black smoke is pouring out, and the whole engine is shaking and screaming. That shaking, that's your pain signal.
Okay, I'm with you.
Yeah.
And oxidative phosphorylation.
That's like switching to a high-tech solar battery setup or a modern nuclear plant. It's steady, it's clean, it's incredibly efficient. It doesn't produce the same toxic exhaust. When you force the neuron to use ketones, the solar power, you stop the coal burning, the glycolysis, and when you stop that rapid, dirty glycolysis, you dramatically dampen the pain behavior.
So you're literally changing the fuel source to calm the machine down.
That's the metabolic view of it, yes. But there is also a purely electrical view. And this involves something really cool called the K-ATP channel.
KATP, so.
Potassium ATP channel.
Right, this is where it gets really interesting for the biology nerds among us. When a neuron burns ketones instead of glucose for various reasons, it produces a little less ATP locally, right there next to the cell membrane. Wait, I thought ATP was energy. Don't we want more energy, not less?
We do, overall. But location really matters here. These specific channels, the K-ATP channels, are like little gates that are sensitive to the amount of ATP right next to them. When that local ATP level drops, which happens on keto, these gates, they spring open.
And when the gates open,
Potassium ions flow out of the cell. And in neurobiology, when positive potassium ions leave a cell, the cell becomes hyperpolarized.
hyperpolarized. Okay, can you define that for us in simple terms?
Yeah. Think of a neuron like a gun with a trigger. In a chronic pain state, that trigger is a hair trigger. You just breathe on it and it fires. That's hyperexcitability. Hyperpolarization adds a heavy weight to the trigger. It physically increases the electrical gap between the neuron's resting state and its firing state.
So it just makes the neuron harder to turn on in the first place.
Exactly. It physically electrically calms the hyperexcitability.
So if nosoplastic pain is that volume knob turned up to 10, the ketogenic diet, through these KATP channels, is effectively installing a governor on the engine so it physically can't rev that high.
That is a perfect way to visualize it. You are raising the threshold for pain to fire.
That is incredibly cool. I mean, that's a direct physical mechanism,
Yeah.
but we're not done with the mechanisms yet, are we? We also have to talk about inflammation, because chronic pain is almost always inflammatory at its root, right?
It is. There's almost always a component of neuroinflammation. And this is where we meet a fascinating molecule called beta-hydroxybutyrate, or BHB.
BHB. That's the main ketone body, isn't it?
Yeah.
That's the stuff that's floating around in your blood when you're in ketosis.
It is, but for a long, long time, we just thought of BHB as fuel, just a carrier of energy, like a little molecular gas can. The new research, which is so exciting, shows it's actually a potent signaling molecule. It acts almost like a drug or a hormone in its own right.
What does it signal? What's its message?
It signals the immune system to basically chill out. Specifically, BHB has been shown to directly suppress something called the NLRP3 inflammasome.
The inflammasome. That sounds like a villain in a Marvel movie.
It kind of acts like one in chronic pain.
Yeah.
Think of the NLRP3 inflammasome as the fire alarm of your innate immune system. In many chronic pain conditions, this alarm is stuck in the on-pan position. It is constantly blaring, pumping out pro-inflammatory cytokines chemicals like IL-1 beta and TNF-alpha. These chemicals irritate the nerves and keep that whole pain cycle going.
And BHB just turns off the alarm.
It walks right up to the control panel and flips the switch to off. It directly blocks the activation of NLRP3, so you get a direct, measurable reduction in neuroinflammation. This isn't just eating healthy reduces inflammation in a vague, general sense. This is a specific molecule binding to a specific target to stop inflammation at its source.
That is just wild. So let's recap. You're changing the fuel from dirty coal to clean solar. You're installing a governor on the engine, the KATP channels, and now you're turning off the fire alarm, the NLRP3 inflammasome.
And there is one more layer. And this one might be my favorite because it connects to something most of us use every single morning. Caffeine.
Okay, I'm listening. What's the connection to coffee?
The connection is adenosine.
Right, adenosine. That's the chemical that builds up in your brain all day. It makes you feel tired. And caffeine works by blocking adenosine receptors so you don't feel tired.
Correct. But adenosine doesn't just make you sleepy. It is a powerful, natural anticonvulsant and analgesic. In simple terms, it calms the nervous system down, it binds to A1 receptors, and it inhibits neurotransmitter release.
So having more adenosine floating around in your brain would be a very good thing for pain.
A very good thing. It acts like a natural brake on the entire nervous system.
And let me guess, the ketogenic diet does something to adenosine levels.
It absolutely does. Research, like the review from Ruskin and his colleagues, shows that a ketogenic diet significantly elevates brain adenosine levels.
So in a way, being in ketosis is like the opposite of drinking a cup of coffee, but specifically for your pain nerves.
Yeah. In terms of that one mechanism, yes, it's a great way to think about it. While caffeine blocks the calming effect to stimulate you, keto boosts the calming effect to settle the system down. And here is the real kicker. This adenosine mechanism is so powerful that it even helps mitigate opioid-induced hyperalgesia.
That's the terrible paradox, where taking opioid painkillers for a long time actually makes you more sensitive to pain.
Exactly. The diet seems to naturally produce a molecule that acts like a powerful brake on the nervous system, doing what we try to do with all these heavy-duty drugs, but by using the body's own internal machinery.
Okay, so we have the mechanisms, we have the theory, it's all very compelling. But does it actually work in real people? Because, mice are great, but I am not a mouse.
That is a fair and essential point. We absolutely need the clinical evidence. And we have a really interesting pilot randomized clinical trial by Field and his colleagues, which was published in Pain Medicine.
Walk us through this study. What do they do?
So they took a group of participants who all had chronic musculoskeletal pain, and they did something very smart at the beginning. They started with a run-in period where everyone just had to remove ultra-processed foods from their diet.
Okay, so step one is just getting rid of the junk food.
Right, a baseline. Then they randomized them. One group was put on a whole food ketogenic diet, so, meat, fish, eggs, nuts, lots of non-starchy veggies, high fat, very low carb. The other group stayed on a minimally processed whole food diet, but one that still included healthy carbs.
And the results? What happened?
The keto group saw significant improvements in their reported pain scores, better blood biomarkers, and improved quality of life scores. They also saw measurable reductions in inflammation and oxidative stress compared to the control group.
And you said a whole food keto diet.
Mhm.
I think that distinction is really important. We aren't talking about dirty keto like eating fast food burgers without the bun and diet soda.
That is a crucial distinction. The study really emphasizes nutrient density. But the key takeaway is that the metabolic shift, the ketosis, correlated directly with the pain reduction.
Which brings us back full circle to Natalie, because her result wasn't just improvement. Her story ends with remission.
Yes, she underwent a strict 3-month medical keto intervention, a total reset. And in her article, she reports being in remission for 10 months and counting.
What I found so incredibly hopeful about her story is that she isn't stuck on a super strict keto diet for the rest of her life.
That's the metabolic flexibility aspect. It's so important. She says she can now eat a pretty normal diet. She even mentions having occasional pizza without relapsing into that chronic migraine state.
That implies the system actually healed. It wasn't just managing the symptoms day to day. It was fixing the underlying dysregulation.
Exactly. Dr. Bills calls it a metabolic reset. The diet stabilized her hypothalamus. It stopped those sawtooth blood sugar swings, and it allowed her nervous system to finally calm down and recalibrate. Once that doom loop was broken, her body could handle normal variations in diet again.
That is the absolute dream for chronic pain patients. Not just management, but a true reset.
And we see validation of this very same principle in Dr. Popola's work, too. Remember the fibromyalgia patients with the hidden insulin resistance?
The brain diabetes group, yes.
Popola took a subgroup of those patients and treated them with metformin.
Which is a very common diabetes drug.
It is. Its primary job is to help with insulin sensitivity. He gave this diabetes drug to non-diabetic fibromyalgia patients. And guess what happened? Their widespread myofascial pain improved significantly.
That is incredible. Treating the insulin resistance directly treated the pain.
Yeah.
That pretty much confirms the link, doesn't it?
It strongly supports the hypothesis. If fixing the metabolism fixes the pain, then the pain was, in all likelihood, metabolic in origin to begin with.
So where does this all leave us? It really feels like we are standing on the edge of a pretty massive paradigm shift in how we think about pain.
We really are. For decades, the dominant model for chronic pain has been manage the symptoms. Here are some painkillers, here's some anti-inflammatories, here's some physical therapy, and, those things have their place. But this new model says, fix the cellular metabolism.
It's moving from just treating the smoke to actually trying to put out the fire.
And looking at the fundamental health of the neuron itself. There's another fascinating piece of research on a gene called OX1.
OX1, what does that one do?
It's a key enzyme your body needs to be able to use ketones for fuel. So researchers created mice that had a mutation in OX1, so they couldn't use ketones. They could only run on glucose.
And what happened to those mice?
They had developmental abnormalities in their sensory neurons. They had issues with how their nerves grew into the spinal cord. This suggests that sensory neurons don't just tolerate ketones, they might actually need access to ketones for proper health and development.
That that implies that our modern, high-carb, constant grazing lifestyle, where we almost never enter a state of ketosis, might be depriving our nerves of a fundamental nutrient state they evolved to need.
That is the evolutionary argument, yes, that we evolved to cycle in and out of ketosis. By never being in it, we may be leaving our nervous systems vulnerable to this kind of metabolic dysfunction.
Now, we have to be careful here. We're not saying keto cures everything, and we're certainly not saying everyone should go out and start chugging MCT oil today.
No, absolutely not. And Natalie Mead makes a great point in her article. She talks about the Pandora's box of hope. When you have been told over and over that you are incurable, hope is a dangerous and fragile thing, but it's also necessary.
Right, you have to handle it with care.
And the science requires rigor. We are talking about medical interventions that impact ion channels, gene expression. There's a whole other layer with something called HDAC inhibition and inflammasomes. This isn't a fad. It's complex biology.
But the distinction, and I love how you put this in our notes, is the difference between the word idiopathic and the word metabolic.
Yes. Idiopathic is just doctor speak for we don't know the cause. It's a shrug. Metabolic means we think we know the cause, and it's something we can potentially change. That is a world of difference for a patient.
It's just the power back to the patient. It's not just accept your fate. It's check your fuel.
Exactly.
So for the learner listening to us today, maybe you have chronic pain, maybe you know someone who does, or maybe you're just fascinated by how the human body works. What does this all mean for you?
It means that if you are dealing with chronic, unexplained pain, it might be worth looking at your metabolic health with a new set of eyes. Look at your blood sugar stability. Look for signs of insulin resistance using those deeper tests like HOMA-IR, not just the standard A1C. And consider that the food you eat isn't just calories, it is information. It is signaling. And changing that signal might just be the key to turning off the alarm.
I want to leave everyone with a final thought to chew on.
Mm.
We've talked a lot about migraines and fibromyalgia today, but if chronic pain is effectively a check engine light for metabolic failure, how many other incurable neurological conditions are actually just energy crises in disguise?
That is the billion-dollar question, isn't it?
If you want to dig into the nitty-gritty details, the KATP channels, the Popola study, Natalie's full, powerful story, we have linked all the sources. Go read them. It is truly fascinating stuff.
Absolutely. Always be curious.
Thanks for diving deep with us. We'll see you on the next one.